What is gravity? We all think of gravity as our attraction to Earth, since that's all we see in our daily life. Or perhaps one might think gravity only applies to planets or big objects, but in reality it applies to everything. Gravity is the natural attraction of all existing masses to one another, so everything is attracted to everything else. Even your burger and fries from McDonald's are attracted to each other by a gravitational force, but it's so small it doesn't actually do anything. It is also worth noting that, as you know from Newton's third law, every action force has an equal and opposite reaction force. And the force of gravity is between the objects. The force the Earth exerts on you is equal to the force that you exert on the Earth. It just doesn't impact the Earth because it is much, much bigger than you, and the acceleration it experiences is therefore far, far less. So, how might we find the force of gravity? The law of universal gravitation says that the force of gravity is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. This is illustrated by this equation for the force of gravity. G is the universal gravitational constant, and it is equal to 6.67 times 10 to the power of negative 11. M1 and M2 are the masses, measured in kgs of course, and r is the radius, aka the distance. It is important to know that this is the distance between the centers of each object, as we consider the gravity to be contained within the center of the object or the center of gravity. What is the gravitational field? The gravitational field is the attraction a mass exerts at a certain radius from itself per kg of mass of another object. Basically, if we put a 1 kg object at some radius from the Earth, the force of gravity it would experience would be the gravitational field strength at that point. As you can see, the field strength equation is basically the first force equation, but without the extra mass, as we simply want to see the field of this object. This makes sense since it is the force exerted on each kg of mass that comes into contact with the field. Hence, one can multiply the field strength by any mass within it to find the gravitational force. Another aspect of this is the gravitational field strength is equal to the acceleration an incoming object would experience at that point. We all know the formula of gravitational potential energy is E equals mg. Wait a minute. This is when we were talking about Earth. If you look at the equation, it doesn't seem quite right when put on a scale that is not Earth and a small body on the surface. Especially since g in the original equation was supposed to represent the gravitational field strength at the surface of the Earth. Let's look at the actual equation. While gravitational potential energy seemed to increase with height, the magnitude, so to say, we can clearly see that the gravitational potential energy is inversely proportional to the radius or distance. Overall, this equation seems pretty similar to the original force equation, except for the fact that we have r instead of r squared, and the energy is negative. But wait, the energy is negative? How does this work? Essentially, as you move farther and farther away from the central object, work is done. If a rocket is launched from Earth, it loses speed and kinetic energy as it moves farther and farther away, and hence the gravitational potential energy is something that is gained with distance. However, only at an infinite distance away from the other object will the rocket not be in contact with the gravitational field. Hence, as the distance approaches infinity, the gravitational potential energy approaches zero. So all gravitational potential energy, G, is negative, as can be illustrated in the graph that has been shown. Now let's take a look at objects in orbit. When something is in orbit around something else, it has both kinetic energy because of the movement and gravitational potential energy because of gravity. If the bigger mass is spherical and the orbit is circular, the object is traveling in uniform circular motion, with uniform speed giving the same kinetic energy, and uniform radius giving the same gravitational potential energy, since obviously the masses stay the same. Let's go over how to find the orbital velocity and orbital kinetic energy. So we'll be using the following equations. The force of gravity is equal to G, big M, little m. Now this is a replacement of the original equation which had m1 and m2, but we're using big M as the central object and little m as the entity orbiting around it. Then we consider the centripetal acceleration equation. AC equals velocity squared over r. Now, we first have to consider that From this, we know that the gravitational field strength is equal actually to the acceleration due to gravity, so that is g big M over r squared. So from this, since these two are equal, we can now get that g big M over r squared equals v squared over r. Now if we rearrange to find velocity in orbit, we get square root of gm over r. Now, kinetic energy. Let's say we want to find the kinetic energy, now that it is in orbit. So, we know that the kinetic energy is equal to 1/2 mv squared. Now this m is a little m, since it is where we know the velocity, we're just trying to find the kinetic energy now of this object that is rotating. So it should be 1/2 m times g times big M over r, equaling to be 1/2 g m little m over r. Now this looks awfully familiar, and I think I know why. This is equal to the magnitude of the gravitational potential energy. So what can we infer from this? From this we can infer that the kinetic energy is equal to negative 1/2, since there's no negative over here, of the gravitational potential energy. Now on to escape energy and velocity. Escape energy is the kinetic energy required to escape the gravitational field. The escape velocity is the initial velocity the body must have to escape the impact of gravity. The kinetic energy would obviously have to cancel out the gravitational potential energy in this situation, making the total energy 0. So you can find the escape energy by finding the gravitational potential energy at that point, and obviously multiplying it by -1, since gravitational potential energy is negative. Let's find the escape velocity accordingly. Since we know that negative kinetic energy is equal to the gravitational potential energy, we can tell that negative 1/2 mv squared equals minus g big M little m over r squared. Sorry, no squared. Hence, if we cancel some things out and move some things around, v squared equals g big M r 2, and v equals the square root of 2gm over r. This is the escape velocity. Furthermore, this achieves the objective of making the total energy equal to 0, meaning there is no longer any impact of the gravitational field on the object. Now let's take a look at binding energy. Now what is the difference between binding energy and escape energy? While escape energy is the energy required to escape the gravitational field, the binding energy is how much additional energy needs to be added to escape the field, aka the work that needs to be done. When you are sitting down in your chair, you may not think you are moving, but the reality is that you are moving in orbit of the Earth. The only catch is the distance or radius of your orbit is equal to the radius of the Earth. Now, this might sound strange, but since the Earth is spinning, if you don't try to move, you will stay on the same spot on the Earth, as you are moving at the same pace that the spot on the Earth is moving. Essentially, you are moving in orbit of the Earth. Hence, you've already got a head start on the kinetic energy and speed. To make the total energy 0, you only need to increase the kinetic energy, by the amount of additional energy required. This would be the binding energy. So, to find the binding energy, we just need the magnitude of the total energy, since we must find the work to be done, or the energy needed to make the total energy 0. As we calculated earlier, in orbit, the kinetic energy is equal to minus 1/2 the gravitational potential energy. Therefore, the total energy is equal to the kinetic energy plus the gravitational potential energy, making it 1/2 the gravitational potential energy. So all that we need is minus 1/2 Eg, and we're all set to go on finding the binding energy. Hope you enjoyed this video and learned something about gravity and gravitational fields.